Looks like we are live. We'll just wait a second. Shelby's watching the feed just to make sure everything's coming through properly. As soon as she says she sees it, then we're good to go. Okay, she's good. All right, so we'll give it a minute for some people to jump on because usually it takes a couple seconds for people to hop on. But thanks for coming. It's nice to have you here finally. And yeah. Okay. Yeah, no problem. It's always fun to have people with many different aspects in research and knowledge talk to the public. So, okay, so we'll give it 5, 3, 2, 1. All right. Oh, so they say they can't hear you. It's probably not on your end. Let me check something really quick. Yeah, check to make sure. It's probably not on you. I can hear you fine. It's just the stream isn't picking up your stuff. Anything yet? Hey, Ben, can you say something? We can test your. Anything, Sheldon? This is always the problem sometimes. It's like there's always one thing that goes wrong, even though it works fine last time. Let's see. Um, I'm going to try to set up another little. No, sorry, everyone. There's always this kind of problem that we have. So just hold on there, and we'll try to get it fixed. Okay. It looks like it's black on there, so let's see what happens when I do this. All right, Ben, can you try saying something real quick for me? It takes like 10 seconds. It could be that it's on Zoom and maybe something changed on Zoom, so it's not picking that up. Nothing. Um, we might, we just might have to switch to a different meeting thing. Let me do that really quick. You have Skype? Okay, 1 second. Ben Bromley. Okay. think so, yeah. I sent you a message. Okay. Okay. Sorry, everyone. We're just trying to get things going again. Good. Can you hear me fine? Okay, let's see if this can pick us up now. It's crazy how things don't work sometimes and then they don't. So. I might have to end the live video real quick. Do you want to type that in there? Okay, sorry everyone, we'll be right back.
Okay. Go ahead and say something and see if we can hear you.
Okay, hello. Hey, it's great to be here with you, Paul.
And good? Okay, looks like we're good.
All right.
Alrighty then. Sorry for the problems, everyone. For some reason, anytime we try to do this, there's always one thing that goes wrong. So, I'm here with Ben Bromley. He's a professor and researcher at the University of Utah Physics and Astronomy Department. It's always a long thing to say. But he's been with the department for how long?
All right. It's
Since,
like over 20 years. Let's leave it at
yeah,
that.
like the mid 90s or something. Yeah,
Late 90s, late
late
90s.
90s. Okay. Yeah. So tell us about what you're doing right now, and yeah, what are you up
Hey.
to these days?
All right. Well, listen, I've spent the last little bit in the outer solar system with a small project in more distant objects. The theme of the last few years of my work has mostly been Pluto and Charon. The Pluto moon system is just beautiful. It is Pluto is a binary planet. Pluto and Charon.
Yeah, that's what I always
Charon's
tell everyone is like, oh, if you want to make Pluto a planet again, you're gonna have to call it binary planet.
That's right. Yeah, Charon's only a tenth the mass of the Pluto, but that's still pretty big.
Yeah.
That's quite a partner to have, and that's all we knew about Pluto back in the 70s and 80s. But with the Hubble Space Telescope, it became apparent that there was more.
Hmm.
Now we know that Pluto and Charon share four moons, small moons. They're tens of miles in diameter,
Yeah.
so tiny little things, chunks of icy rock. Styx, Nix, Kerberos, and Hydra, and they are beautiful. This Pluto and Charon orbit each other every 6 days, roughly, and these four other small moons orbit in kind of harmonic fashion,
Uh-huh.
close to resonance of 3, 4, 5, and 6. So every time one of these like Styx, the innermost moon or small moon goes around Pluto and Charon once. Pluto and Charon orbit each other 3 times, and that kind of setup, that dynamical orbital setup, is just beautiful and really hard to create. So there are a lot of lessons in understanding where Pluto, Charon, and their moons came from. Those lessons apply to binary planets. Excuse me, binary star systems elsewhere in the galaxy and the universe. And so understanding Pluto and Charon will give us some insight into how planets form around binary stars. Most stars in the galaxy are binary, so we're not talking about anything rare here. We're talking
Yeah.
about a process that might happen, all the time, all everywhere.
Yeah, I
So
remember like hearing probably 10 or so years ago before they started looking at being able to see stars and stuff a little bit better. They were talking about how it seems to be almost impossible to have planets around uh, double or triple stars and stuff like that because there's just so many dynamics that go on. But it seems like the more that they find more stars and able to hone in on like different setup or not setups, but different systems, they're starting to see that there are planets around these double star systems, and they're like, oh, okay, well, that's cool.
yeah,
But
Tatooine is a real thing. Or
yeah, so uh, when they released that picture of Pluto from the the New Horizons,
Mhm.
I bet you were pretty happy about that, right?
Yeah, that was really cool. The whole thing was really exciting that we were able to actually, put a mission out that far into the outer solar system, and to get so close to seeing Pluto and Charon is just beautiful. And the pictures of the small moons, Styx, Nix, Kerberos, and Hydra, just stunning. I mean, the whole thing is just amazing. So
Yeah,
yeah, we learned an awful lot from New Horizons, and much of our work was focused on trying to extract more from the New Horizons mission. Now that we've actually visited Pluto in that
yeah.
way.
So I think what we learned most is that we need to send something back there, right?
Yeah, it's always good to do. Yeah, but the mission was incredible. We didn't have a sense of the rich geology that we now have,
Yeah,
and it resonates back to us. It turns out that there's an extrasolar traveler, an interloper, a little chunk of something that came through our solar system. Almu, I'm probably not pronouncing it right.
that's
This
as good as I could do.
okay. The This is a body that was traversed the solar system just a couple of years ago,
Yeah,
and it was going too fast to be bound to the sun. So it came from somewhere from a distant star, and just happened to pass through our neighborhood. And it's a strange thing. It's a has a seems to be very, very light, and not very dense, and shaped weirdly, either like a frisbee or a very long needle.
yeah. I saw the newest thing with that was it kind of looks kind of like it's more flattened out and wider, and I was like, oh, it's like the Millennium Falcon, and it's just drifting along through space right now.
That's, that's, that's right. Yeah, and one of the ideas, a recent idea, I was that really it's this flattened thing is a chunk of some of nitrogen ice sea from a planet just like Pluto, but
Yeah,
one out there around some other distant star. Very cool. So it
yeah.
all wraps around. Pluto's awesome.
So like that kind of leads us like there was a few things that you talked about resonances and even objects that are even farther, and that's kind of what we're looking for to talk about today, and that's the Planet Nine, as everyone likes to call it. Um, and so that's our goal tonight is talk about that. Uh, but it's probably best to talk a little bit about the background, like how like researchers and stuff come and find these things and what has led to the development of something being out there. And like a long time ago, we were looking at things like Uranus and stuff, and noticing that there's something with Uranus tugging on it, or something that's causing a disturbance in its orbit around the sun, and that kind of led to the prediction of Neptune, right?
Absolutely.
And
Yeah.
so
Yeah.
it's like that kind of stuff is still being used today, and that's kind of the idea behind why some people think that uh, like a Planet Nine that's hanging out farther beyond Pluto is that it could be something out there. And so, do you want to talk a little bit about how you come to that conclusion for Planet Nine based off of kind of like the ideas of what happened before?
Sure. Yeah. Yeah. You mentioned really nicely the prediction of the existence of Neptune based on the orbit of Uranus, and that is like an amazing theoretical coup. You know,
Yeah.
um, when the theorists can tell the observers where to aim their telescopes and then find something, that's a good day for theory for sure. And something similar happened with with this so-called Planet Nine. Now, I have to kind of give a little bit of a historical context. You know, back in the day, people were concerned that Neptune's orbit was also kind of wonky, suggesting that there might be a planet beyond that. And I'm talking around the turn of the 20th century. Um, and people began to suspect that there might be a planet X.
Hmm. Oh, hold on. It looks like you froze real quick. Oh, it looks like
Some
Ben froze up. Ben, can you hear me? Hold on, everyone. Let me.
something massive, well planned, and the
There we go. Okay, so you're back now.
oh, sure.
Okay, so can
Yeah,
you
so
repeat like that last 15 seconds?
okay,
Sorry.
sure. The people thought originally that Neptune's orbit was a little bit wonky and began a search for some other more distant object known as Planet X. That it turned out that Neptune's orbit was just fine, and yet there was another planet out there. Um, which was Pluto. It's a dwarf planet, but it was discovered in the process of searching for something bigger
Yeah.
in the outer solar system. And so then that was in the 30s, and fast forward to I think probably 2014 is when the story of Planet Nine begins. People began to notice that there was a correlation in the orbits of some of the more distant objects that were seen, things like Sedna and these icy bodies in the outer solar system. They are
So,
all on eccentric orbits. That's the big deal. They all come fairly close to the sun, well outside the orbit of Neptune, but we see them when they're close in, and then they traverse over thousands of years into the outer part of the solar system.
so like when you're
Right.
talking about Sedna, these are objects that exist beyond Pluto and Neptune's orbit that have been discovered in like the last 30 years or so. Um, and so there's a few that are close to Pluto's size that hang out there. That's right. Is that right?
Yeah, yeah, that's right.
And so
Um,
like it's just like this kind of like and it's a slow discovery process because they're so faint and they're so far away that you kind of have to look for these little tiny dots in between multiple days on images and see if something's shifting. That's kind of like how these were found, right?
yes, exactly. And so people are just mapping the solar system and looking for things that move in specific ways across the sky.
And how many have
And
we? How many have been discovered so far? Do you have a ballpark figure now?
oh, I should know. I should know how many of these trans-Neptunian objects are out there. The really distant ones are numbered in dozen or so, but there are thousands of these smaller objects. I should know what the total is. People have made certainly estimates of the total mass of the small objects out in the outer solar system. It's not much. It's sort of more lunar mass. Not you don't have a Jupiter's mass worth of stuff hanging out
Right.
there.
Yeah. So these are often called like trans-Neptunian objects, and
Yes.
some of them are like minor planets. And then Pluto is like it's funny that Pluto fits into like three different categories now. It's like a dwarf planet, a Plutoid, a minor planet, and a trans-Neptunian object now. So it
Yeah.
moved from just being called a planet to having four classifications. So it's like, oh, we didn't kick it out of the planetary lineup. We just added it to a bunch of others. It gave it more friends. So,
Yeah, that's exactly right. Yeah. Yeah.
but yeah, they're all like they all hang out like the ones we're looking at for the effects from so-called Planet Nine are these ones that are fair amount farther out there than Pluto, right? Do you have an idea of like how much farther they are than Pluto?
Well, Sedna is my favorite of these, and if I remember right, Sedna's spends on average the time at a distance of roughly 500 times the Earth-Sun distance. So 500 AU, if I remember right.
So
It's
500,
possible.
500 times 93 million miles. So
Yeah, yeah, it's a ways.
yeah, it's a
And
little bit out.
we only see these things because their orbits are eccentric, meaning they come close to the sun in one pass of their orbit, and then they travel very, very far out and more slowly, just following the laws that Johannes Kepler derived. And so they all come with these, big sort of oval eccentric orbits. And when you start to map them out, you expect just sort of shrugging your shoulders and thinking of how do you arrange a bunch of oval shaped things around the sun. You kind of expect them to be scattered all over the place, right? There's no reason why Sedna's orbit should be related to 2012 VP113. Why should they be related? Well, it turns out that they all were kind of clustered on one side of the sun, which is really, really surprising. And this has led Trujillo and Shepard to astronomers to suppose that there's something big and unseen that's actually shepherding these things to kind of corral the orbits of these distant Sedna-like things together. And the mass required, sort of the orbital characteristics needed to do that shepherding was substantial, tens of Earth masses, and the distance had to be pretty far out there. Otherwise, we would have seen it. It's not right next to Neptune. So that was the original inspiration for the hunt for Planet Nine. And then Batygin and Brown in 2016 really began to put together the Planet Nine hypothesis. They made it, in some sense, more formal, I think is fair to say. Running simulations to understand more precisely where something might be in order to corral the orbits of these smaller things that we see.
Right. That's pretty cool. Just so everybody knows, if you guys have any questions or anything like that, feel free to put them in the comment section. And then when they pop up and we get a chance to throw them in there, you're welcome to ask those, and I'll pass those questions on to Ben, and he can answer them as best as possible. But yeah, so like this shepherding process, like you're talking about how exactly does that little shepherding process work? It's not like it's purely gravitational tugging type of thing, right? So like kind of how our moon tugs on the Earth and causes it to change orbit over a small amount of time, but then it starts to build up a resonance, so it doesn't actually affect it to cause big changes in orbits or spin rates and stuff like that over a really long time, right?
Yes, yeah. And for the phenomena that I'm thinking of here for Planet Nine is a fair part gentle and subtle. The distances are so vast. Really, the sun is the only thing that most bodies feel at any given moment. But the effects are seen over long periods of time, millions of years. Sedna, even though it doesn't get very close to the inner part of the solar system, is affected by Jupiter, for example, and Neptune. The slight gravitational tug from those bodies, just by virtue of their being near the sun, kind of shepherds or will cause Sedna's orbit to precess. So meaning that the elliptical pattern that it forms will kind of rotate, like the hand of a big, broad hand of a clock, in
So it's
time.
like if you have an egg sideways, it's kind of twisting the egg around like this, right?
Yeah, it's just like the egg is spinning, although the spinning point, the axis that it spins on, is really toward one side where the sun
Right.
is. But yeah. So it kind of will look like petals of a flower if you take a snapshot of the thing in time.
Right.
But the presence of something else will kind of modify how that precession takes place. And so just by, even without a resonance necessarily, some, concerted dance between something like Sedna and Planet Nine, just by virtue of having Planet Nine out there, it will kind of cause the precession to be modified and guide Sedna so that the orbit more or less lingers in a direction determined by Planet Nine itself.
Gotcha.
Now, I have to say that what we're looking at is a pattern of orbits in these really distant things.
Mm-hmm.
And this pattern, starting with Trujillo and Shepard in 2014, inspired a lot of people, including me, to go looking for Planet Nine. I mean, it'd be amazing, right?
Yeah.
You find a big thing like 30 times the mass of the Earth in the solar system. That's the stuff of breakfast placemats, right? When kids are learning what the solar system is like with the planets listed, it's huge to discover something like that, and to try and figure out how it got there really tells us about what the solar system or how the solar system formed. So this pattern has the property that we could just have been lucky to find all these bodies lined up the way they do. I mean, lucky or unlucky, I'm not sure how you want to look at it. It could have been just by chance. People are thinking not, right? There's been a lot of work to try and understand an answer to the question, is it just by chance, or are these alignments between these egg-shaped patterns really indicative of some real physics? People really worked hard to come up with an answer, and it still really is at play. It really looks like some shepherding body is needed, but all it takes is like one or two discoveries of small bodies that aren't aligned to just blow up the whole thing.
So, like part of the thing is like maybe we just don't have a big enough sample, and if we do find more that are like in this same thing, that'll give this whole idea even more strength. But if we
Yes,
find others that kind of don't fit this, it loses strength and kind of goes a little bit farther away from being a single body causing this.
that's exactly right.
So
Yeah.
if it's not something as large as a 30 mass Earth, what are some of the things that it could be that are still causing this, but maybe not something like that?
Well, that's a great question, and people have postulated various things. One idea is there really is more mass out in the outer solar system than we believe, but in the form of many, many smaller bodies. And that's a possibility that could cause the alignment that we observe in the orbits of Sedna-like objects. The other possibility is that, well, of course, just chance alignment, or perhaps things were aligned relatively recently by some event like a passing star, which I'm not sure if that's likely or not. I'm just kind of throwing that out there, but that's it's a kind of thing that can impact the orbits and kind of cause them all to line up in a certain way. Some rapid time event, well, rapid, astronomically speaking.
Yeah.
Then there may be small, multiple smaller planets could be a possibility. There are ways in which to leverage not necessarily big Planet Nine-like objects, but smaller individual planets, which I find still exciting.
So instead of one big Planet 9, it's like Planet 9, 10, 11, 12, 13, 14, and 15?
I suppose it could be, yes. And then, or perhaps maybe not something 30 Earth masses, but something smaller, but placed more precisely in a way that could explain the orbits.
Gotcha.
So really the two choices are that there's, I'll go with three choices. Either there's really a Planet Nine, or there's some mass that we don't know about that's distributed more broadly in smaller, more numerous bodies, or something that we don't understand happened. Either that might be chance observations, or some other event that took place, like a flyby.
Is it possible that these particular objects may be like from another solar system that kind of got cut up by ours, and maybe they're just like a cohort of leftovers from another solar system that got trapped by ours?
Oh, well, that's like one of my favorite questions. Yeah, I worked on the idea that even Sedna itself and some of these other things were captured in the early days when the sun had nearby stellar partners.
Uh-huh.
The sun was born in a cluster of stars 4.5 billion years ago. And so the sun encountered a bunch of other stars early on when it was just forming its planets.
Yeah.
And it's possible that the sun and some close star, because it did have many neighbors before the cluster kind of dispersed, the sun gravitationally tugged on the planetary system of a passing star and brought that material in. And that would initially line everything up. And when I first got that result in a simulation that I did a number of years ago now, I was super excited, right? Because it would be the smoking gun of captured kind of alien planets. But unfortunately, without something like Planet 9 out there shepherding the orbits, those orbits get randomized. The perturbations from Jupiter and Saturn and Neptune cause that precession effect we talked about earlier. And so you really have to have an explanation for why that pattern persists today.
Gotcha.
We don't think they were a flyby, a recent flyby is a really viable option, but you never know.
Yeah. So there was another thing I read recently, and this is kind of like more on the hypothetical side, and that it could be there's a small black hole that sits outside of Pluto's orbit, and it might be a black hole that's doing this, and this could be like a small black hole with like that's even farther away with like the mass. It'd have to be probably 2 times the mass of the sun in order to be a black hole, or maybe a primordial black hole that just stuck around for a really long time. But what's your thoughts on that? Like, what is the possibility of having something like a black hole that's hanging out around our sun long enough for it to cause these formations to occur?
Okay, yeah. I mean that's sort of fun idea, that there's a primordial black hole that's really the source of the correlations that we see in the these planets, these small planets in the outer solar system. I do caution adopting models like that. I mean, yeah, it's always great to have a black hole. When black holes are involved, it is awesome. I love black holes. Our galaxy, the Milky Way, harbors a 4 million solar mass supermassive black hole. And stay tuned. The Event Horizon Telescope will be snapping a picture of it and releasing it soon. I expect, just as they did with this really big supermassive black hole in the galaxy M87. You may have seen those images.
Yeah.
So when black holes are involved, that's great. I caution, however, that having a black hole at the right place at the right time, in the outer solar system, doing the work of a 30 Earth mass planet is something you have to kind of worry about a little bit.
Yeah.
It turns out that planet formation is really robust. It may be that primordial black holes are out there too and are all over the place, but it may not be. We've never seen a primordial black hole at the level of being able to point to it and say, look, there's a primordial black hole.
Right.
We have seen many 30 Earth mass planets in our search for exoplanets.
Yeah, we've had a lot of those.
Planet formation happens.
Yep.
It's just amazing. It's a very robust process. When stars form, they form a disk of gas and dust. That gas and dust chemically and gravitationally glom together, and planets form readily. And I have to admit that as a theorist working on planet formation, I missed an extraordinary opportunity. Right. Because in around 2010 or so, we began running simulations of the formation of Jupiter. Jupiter was formed in our models roughly where it is seen today, 5 times the Earth-Sun distance. And it started off in a part of the solar system that had lots of solid material as well as gas. Because it was beyond the so-called snow line, there was a lot of ice of different forms. Methane ice, CO2 ice, and just more than water ice. So there's all this stuff out there to glom together and form planets. So Jupiter's precursor very quickly formed a core, like an icy core, and then began to accrete gas. But it wasn't alone, and our simulations showed this. There were other icy cores out there, and they were pretty substantial. They were, good, 10 Earth masses or so, 5 Earth masses, and they were also capable of accreting gas and becoming Jupiter. So there was this competition, though, because there's only so much gas and so much material that you can accrete. And as these things grow, they begin to orbitally interact with each other. And it turns out that the biggest thing in the picture wins. Right? Jupiter was the biggest thing in its domain, and it accreted, it merged with and gathered up smaller things around it. And those smaller things were pretty big. But sometimes it didn't always just eat them up. Sometimes the encounter between a growing Jupiter and a growing wannabe Jupiter was close, but but no collision. And the outcome of that would be that the lighter body would get thrown way into the boondocks of the solar system, or perhaps ejected from the sun altogether to become what a rogue planet, I think they call them.
Yeah.
So we saw this stuff happening in in our simulations, and we kind of we reported it. It was cool, but we failed to make the prediction that there's one of these that could be out there in the outer solar system. So our simulations sort of show that the formation of Jupiter produced this fountain of smaller stuff, things that didn't become Jupiter. I mean, Jupiter's 300 times the mass of the Earth. It's a beastly thing.
Yeah.
And it chucked away a lot of stuff in its formation, as well as accreting a lot of gas. So that we see this kind of thing happening before we even knew about Planet 9, this kind of process as a regular part of planet formation. And we see 30 Earth mass planets around other stars with fair frequency. That means that this, it's a pretty reasonable explanation. So I don't know, weigh it out. Primordial black hole, that's very cool. Or, a scattered,
it's
giant
less
planet.
likely to be the
Yeah.
and like the primordial black hole, it's been around for so long. What's to say that there's any of those left that haven't been accumulated into other things because of all of the stuff that's out there? Whereas something that happens on the lifespan of our solar system is, that's our solar system is way young compared to the age of the universe, relatively. But so it's much more likely that something like your situation would happen in the lifespan of our solar system. It seems to me a little bit more plausible that it's something like that instead of a black hole or something. But
I'm with you. A black hole would be really cool, but I would stick with the possibility. It's for me. I have a clear vision of how we could get a planet out there.
Yeah.
How something like that could happen. It's less clear to me how you place a black hole of any sort right where you need it to be responsible for these dwarf planet orbit correlations.
Yeah. So what would be I just had a thought. What would be the mechanism for that Jupiter ejection to be able to stick around the solar system long enough to be able to cause the shepherding to happen? Would it have to come come close to another body to slow it down in its orbit so it doesn't fall all the way back down to Jupiter, basically, or catch a tighter orbit around the sun? What would have to happen for that to stick around in that portion of the solar system?
Oh, Paul, that's just a fantastic question, and that was a few months of my life. Yeah, that's it. That's exactly the right thing you need to ask, right? Suppose Jupiter, when it grew maybe to 100 Earth masses and could really eject things or accrete or eject things around it. Suppose it ejected a 10 Earth mass planet. And that 10 Earth mass planet traveled, I don't know, 1,000 astronomical units before it returned again. But where would it return? Pretty much where it came from, which is where Jupiter is. So if it did return back to Jupiter, if this happened repeatedly over billions of years, Jupiter would do something with it. It would either accrete it, or it would throw it toward the sun, or it would, scatter it on some other orbit, more likely be ejected altogether from the solar system. So something else had to happen in order to preserve the orbit and actually place Planet 9 in the outer solar system. And in my view, all this happens, all the scattering that put Planet Nine out there in the first place, if it exists, I should say, the scattering, all that scattering took place as Jupiter was growing, which is inside the first million or so years of the sun's formation, because that's the only time when there was plentiful gas in the protoplanetary disk around the young star. In time, the sun's protoplanetary gaseous disk faded. It's likely that it faded from the inside out. We see that happening around other stars. The sun's wind, radiation kind of eroded the gaseous disk from the inside. So picture this. You've got a growing Jupiter, throws a 10 Earth mass planet way into the boondocks of the solar system, where that planet then encounters gas. Okay, because there was still gas around in the outer part, and then that gas could cause a drag on that planet, and that would kind of transform its orbit into something that was more distant. And over several orbits, over millions of years, as that gas dissipated, the planet would settle in the outer part of the solar system. In all my models, and I did this with a collaborator, Scott Kenyon, so it's really our models. In these models, Planet Nine settles, but does so pretty much on an eccentric orbit. It's hard to settle it way out there, 500 or 600 astronomical units where it's thought to be. It's hard to settle it out there with gas that's dissipating on a circular orbit. It's just difficult. The dynamics don't favor that. The gas is kind of eroding from the inside out, and it's not a really strong effect. So it seems more plausible that if Planet Nine is on an eccentric orbit, the model that I've just described, boom, that's the one. My collaborator, Scott, has a different idea. I was a big fan of this scattering thing, but Scott has another really cool idea. And we worked on this together, but he drove this one. It's really fun. You don't necessarily have to scatter Planet Nine to make it out there. You can actually build a planet way out there. And his idea is you have this gaseous disk. Remember how I said it erodes from the inside out from stellar winds? As that gaseous disk gets eroded, the dust that's in the disk kind of gets trapped and follows the inner edge of the disk all the way out. And at some point, if the dynamics get, if the disk sort of stops evolving, that dust and the gas just goes away, the remaining dusty solids can glom together and form Planet Nine. And if it works that way, then Planet Nine will be on a perfectly circular orbit at, 1,000 AU.
It would look something similar to like the pictures of Fomalhaut and the planet that sits in that dust ring that's around there.
Yes, with the exception that that dust ring will be perfectly circular in Scott's model.
Gotcha. That's cool.
That's super fun. Hey, great question.
Yeah, no problem. Yeah, so that kind of gets over most of like the ideas that I've at least heard of for Planet Nine. So is there anything else that like you can add into it to either push Planet Nine towards existence or push Planet Nine toward out of existence?
Okay, well, the theorists, including the work that Scott and I did, have kind of weighed in. We know how to make it. We have a reasonable pathway to predicting a Planet Nine, or at least explaining it if it's observed. Okay, so now we're back in the observer's court. All of this is going to boil down to whether or not we can detect it. And there's a really legitimate question that's concerning, why haven't we detected it already? And the answer would be that it's, possibly we're just unlucky. Maybe it's in the part of the sky that's really crowded with other stars, for example. Maybe it's not quite in the orbit that we expect. Maybe it's highly inclined relative to the solar system. And thereby we're kind of looking in the wrong place because we kind of expect it to lie roughly within the confines of the plane of the solar system, where all the planets are more or less orbiting together.
Could like the albedo of it be a problem? Like, because I know there's a few moons and stuff that are really, really dark. So if it's really dark, it makes it that much harder to locate.
Yeah, and that's the beauty of a black hole, right? You
Yeah.
just will never see it. Exactly right. If it's really uh, unreflective, it'll make a hard problem even harder. This thing is really far away. If you think about how the sunlight has to go to brighten it up, that's one factor that you've got to worry about. So it's going to be really dim on its own, and then all that starlight has to travel back pretty much to where we are, almost next to the sun again,
Hmm.
by comparison. So it's super, super faint. It doesn't keep us from looking,
Yeah. We do
right?
have a
And
question really quick.
oh, cool.
Joan asks if it exists, Planet 9 is between the Kuiper belt and the Oort cloud.
Yes, great. Absolutely right. Yeah, the Oort cloud is a reservoir for of material in the outer solar system, really far out. I think that people are beginning to call things like Sedna and objects that are very distant like that inner Oort cloud objects. Um, Sedna may not be one of those. I apologize. I should be careful there, but that's right. So there's the Kuiper belt, which includes all these trans-Neptunian objects that you mentioned earlier, the things that we're observing. And then the Oort cloud is out there, and Planet Nine would be right at the boundary. Or
So you mentioned distance earlier. I think you said something like 5 to 600 astronomical units. Is that how did you come up with that number? Is that something the number that you would have to have in order for a 30 mass uh, body out there to cause what you're seeing, or how did that number come about?
that's exactly it. Yeah. So you figure out how big a mass you need and where you need to put it in order to explain the correlations, and you do that in simulations. So you set up all the known orbits of the dwarf planets that you're observing in the outer solar system, and you're running simulations and seeing what impact does your simulated planet have on those observed orbits. Do they continue to precess, thereby maybe you don't have enough mass? Do you have too much mass? Are you maybe even ejecting some of these things over time? You can imagine if you put another Jupiter out there, you're going to cause real problems. So the mass of the planet, the putative planet, and its orbital distance and eccentricity are all determined and derived really from simulation to try and map out where you could put something without A, destroying the outer solar system, and B, actually doing something to it.
Yeah. So this is like a best fit model for size and distance that that people were able to come up with, right?
Yeah, yeah, that's it.
Gotcha. Okay, that's cool. Um, so can you talk a little bit about how you do your simulations? Because there's a lot of people that talk about the simulations themselves and running them, but what are some of like the ideas that you have to be able to run a simulation? Like, how do you actually do that?
Oh yeah, yeah, that's a great question. So um, I can kind of walk you through a simple way of doing this.
Yeah.
For one, you'll need to kind of get a hold of a programming language and just sort of wrap around being able to use it. And right now, the entry into programming and coding is really nice. The students at the university take an introductory class when they're in our department in physics that gives them exposure to how to use a programming language called Python. Python comes with it a whole bunch of libraries that you can call. So much of the heavy numerical lifting is actually done for you. So when you have kind of adopted a programming language and can do things with it, read in data and call functions, then your next step is to go out and get data. And NASA has a resource that can provide you the positions of all known bodies in the solar system from the Jet Propulsion Laboratory. So you can download positions and velocities. And all I mean there is just numbers. 3 coordinates gives you a position, and 3 speeds gives you velocity in the cardinal directions. right? So you can know everything about the solar system that you care to simulate. And when you load this data into your, Python code, you can call algorithms and set them up. It's not exactly plug and play, but it's not hard to set up the system so that you can code in the laws of physics, basically Newton's law of gravity, and code in an orbit integrator that actually steps things in time. Given a position and a speed and a force, you can predict where something will be at some small time later. And you repeat this process for all the things that you're simulating. For example, if you've got the sun on board, you've got the Earth and Jupiter and Saturn and Sedna and Pluto or whatever you want. Planet, you have to put in your own Planet 9, by the way. You can run your code forward in time or backward accordingly. So that's I hope that gives you a sense of how this is done.
Yeah. So how much difficulty is it, like having so many different bodies running all at once? Like, do you have to cut some out or average some of them together, or can computers and stuff handle like all of the little bits and forces and everything that are required to get a more accurate picture these days?
Yeah, you have good resources with orbit integrators, just things that solve equations for you to help make those predictions very accurate. The difficulty with the kind of work that we're doing is not so much the number of bodies, because the things that matter in the solar system are not many. You just got to account for, a really crude approximation is the sun, and done. But you really should include Jupiter, Saturn, Neptune, Uranus, and if you're worried about the outer solar system, that's pretty much it. Everything else is very low mass. So then those are the numbers of things that you have to worry about is small. You can try and simulate many other things, but you're only simulating their interaction with this small number of things. The real challenge is that while the numerics are kind of plug and play in terms of stepping things forward in time, you have to step things forward for a really, really long physical time. In order to understand the impact of a planet 9 on the outer dwarf planets like Sedna, you have to evolve your simulation, let it track, thousands or millions of orbits to really get a sense of how things interact. The processes and interactions are slow, but they're important. They build up over time. So that's the real challenge. And that's in comparison to other kinds of codes, like cosmology codes, where you really have to deal with a gazillion particles and they all interact with each other.
Yeah.
And you're trying to track how galaxies form. And ideally you want to track individual stars, and you've got 100 billion stars in the Milky Way, right?
Yeah.
And you're not even talking about the dark matter particles. So yeah, those are challenging, but you don't have to run those in such detail the way you have to work in the solar system. Just to give you a sense of it, if you're interested in tracking the dynamics of Pluto, Pluto orbits, and Pluto and Charon orbit each other every 6 days. They've been doing this for 4 billion years.
Yeah.
That's a lot of orbits.
Yeah.
That's a real challenge for a code that's.
So, in order to run this stuff, is this kind of like the level of computation that you can do on like a home computer, or is this at the level where you actually have to have something more on like a supercomputer type thing in order to get it done in a quick enough amount of time that you're not like, okay, well, I've been waiting for my code for 6 months now, so.
Yeah, that's a great question. You can check the impact of Planet 9 on some model for Planet 9 on the orbit of something like Sedna, including Jupiter and Saturn and Neptune, Uranus. You can do that on a laptop.
So it's
You could
something like,
probably do it on your cell phone. I don't really know.
yeah, so like if a high school student or something wanted to just play around with some simulations on that, do you have any resources that they could do this kind of more of a basic simulation to get an idea of how that works? Are there any like resources out there that they could just play around with this kind of stuff
Oh,
with?
there must be. And with apologies, I do not have them at my fingertips.
Oh, that's fine.
I've got built up my own code over the years, and that's what I use. And I haven't paid much attention to all of the many things that are out there already. But I urge you to check it out. Python has an incredibly uh, you know kind of robust set of tools that are available. NASA probably provides guidance
Hmm.
for activity like that, but I urge you to do it because it is it's yours. It'll take effort, but you can do it.
Yeah. We do have another comment. So Debbie says some astronomers believe that Pluto was kicked out by Neptune due to an interacting celestial body. Um, that's a possibility. Like the reason why it kind of hangs out in the orbit that it does is due to an interaction between it and something else.
Yes, yeah, no, that's great. Um, that's right. I'm given that I focus on Pluto, I've been looking more at what Pluto is now and the formation of its moon system. But Pluto's interaction with Neptune is really interesting. I think that a way to describe what's going on there might be as follows. Pluto possibly formed out beyond Neptune, roughly where it is now, and Neptune may have been in a position closer to the sun on average when it was formed. It was easier to form big objects closer to the sun, where Jupiter and Saturn are. And Neptune may have had more luck in its formation processes if it had formed closer to Uranus, just closer in. And then interaction with the solid debris and gaseous disks, and maybe even changes within the orbital architecture of Jupiter and Saturn themselves, kind of pushed Neptune outward. And Neptune scattered various things as its orbit expanded. Some of these smaller bodies, including Pluto, may also have been pushed out by it. So, and every time Neptune interacted with one of these smaller things, it tended to move out further. So it's kind of a dance between Neptune and this sea of smaller bodies. And Pluto ended up getting trapped in a resonance with Neptune. So in some sense, Pluto is a really, really loose, should be careful, loose moon of Neptune. They're not together, but the orbit of Pluto crosses inside of Neptune's.
Right.
For a time, Pluto is closer to Neptune than it's closer to the sun than Neptune. So for every 3 orbits that Neptune takes around the sun, Pluto takes 2. So they're kind of in this eternal dance together, and that is something of their story. So it may be the object that really scattered Pluto was Neptune itself.
Gotcha. So that kind of just reminds me is like sometimes every once in a while the Earth kind of gets like a temporary moon from something traveling around the solar system, kind of gets trapped gravitationally around the Earth for a few days and then kind of flies out again. But this is the case where potentially that Pluto did something similar, but actually got caught up instead of getting flung out. And so it kind of like was tugged into orbit by Neptune and just kind of hung out there forever, right?
Yes, it's a nice stable orbit. And that's right. And the mystery for me is how Pluto inherited Charon,
Uh huh.
because that's not something that is incredibly easy for me to sort of explain or understand. Why is it a binary planet?
Yeah. So, like, if they were to do some more geologic studies with that to see what kind of similarities and stuff that they may have, it might help explain potentially where it came from.
That's it. And that was one of the goals of New Horizons, I think, to great success. They're really understanding the geology of the two. And so the current model that people use to explain the binary is that it's possible that the formation processes that brought all the material to within Pluto and Charon together happened close to each other, and they started off loosely bound to one another, and eventually they kind of coalesced with Neptune's help. It turns out or perhaps Charon was a free-floating trans-Neptunian object, just like Pluto, and it just smacked into Pluto by chance. And the collision that Charon's precursor had with Pluto was grazing. And so that grazing collision just spit out a bunch of debris, but it ended up letting Charon be captured by Pluto. And the two of them then eventually circularized, and they're in this tidally locked dance now.
Cool. We have another question. So, if you could design a satellite or telescope to help you search for Planet 9, what specifications and instruments would be ideal?
Oh, wow, that's a great question. I should be more thoughtful with this, but there are some really cool things that already exist that may well help us. And I just want to put a plug in for one of them, and this would kind of be leading to my ideal setup, which may already exist. So when I heard of Planet Nine, we meet every week with the astronomy group and go over papers, and I was just super excited about it. And I was talking to one of my colleagues, Kyle Dawson, who you've spoken with here, and we realized that Kyle knew someone who was interested in looking for Planet Nine in a satellite that NASA has put up called the WISE mission. And WISE is it's like the Wide Field Infrared Survey Explorer. I think is
sounds right.
Sounds like I should know. But WISE is a phenomenal thing because it maps out the sky constantly. It's orbiting the Earth and it's kind of spinning on its axis and it's taking pictures of the sky all the time. And so it's snapshots and kind of tumbling on its axis, sweeping across the sky. And as the Earth orbits the sun, that sort of sweep that WISE gets of tumbling on its axis scans the entire sky, and it's been doing this for quite some time. I think almost a decade. And so it has taken pictures of the sky in infrared light. And those pictures are out there for people to study and explore. And I worked with a friend of Kyle's named Aaron Meisner, who was a postdoc at the time. And Aaron identified objects in WISE, and I tried to link the objects that he identified into an orbital pattern. Trying to find that these snapshots, were they consistent with a Planet 9-like body in the outer solar system? So that satellite was perfect. It took snapshots all the time of the entire sky, and we used that WISE data to constrain the existence of Planet 9 in the infrared waveband, which unfortunately is not ideal. We'll get to that in a sec. But we were able to map out the sky, or a good fraction of the sky, and say, we really didn't find Planet 9 here. Now, this comes to your idea that Planet 9 might be dark. It might not reflect light well. Well, in infrared, it's even worse. Infrared light is it's not really expected to be an infrared source. The sunlight is infrared is associated with heat sometimes, and a planet way in the outer part of the solar system would likely be very cold and not a very good infrared emitter. So it wasn't, we were disappointed, of course, because we would have loved to have found it. And in some models, it would glow. Neptune is hotter than it should be, for example, but we didn't see it. So I guess my ideal thing would be like the WISE satellite, but in an optical waveband, where we're looking. Now that brings me to the European Space Agency's Gaia mission. Then Gaia has monitored billions of stars, and it's out there mapping the sky all the time too. So and Gaia has a solar system component to its observational program, so it may well be a great resource in the search for Planet 9. Other ways of looking for it involve the ground. The Kyle Dawson's team is mapping out stars and galaxies. they take snapshots of the sky regularly. And if you take a snapshot of a sky, multiple times in a night, you will see motion in a Planet Nine-like body, because the Earth's movement will lead to kind of a parallactic, a perspective shift, and so you'll see the position of Planet Nine differ from where you'd expect it if it were a distant star. So, and I know there are people who are looking for Planet Nine in that way too. It's pretty exciting. If I had to guess, I think it's hiding in a very crowded stellar field. But even that, people are beginning to figure clever ways of finding it.
Yeah. Awesome. Well, it's been about an hour, so does anybody have any questions? Just so we can maybe see if Ben needs to get going or something. But while we wait for some questions, you have anything else to add? Maybe like something about how students can get involved with some of this, or what kind of resources that maybe a future grad student could have at the U if they wanted to come here for something like that.
Oh, yeah, yeah, yeah. No, the uh, Department of Physics and Astronomy is a really fun and exciting place to be with regard to research. And one of the really great things for undergraduate students and graduate students alike is the opportunity to join in on some amazing projects. I'm in on the Astro side of things, and I just do want to put a plug in for the astronomy group without at all neglecting my colleagues in other areas of physics. There's really exciting physics in high energy theory, in particle astrophysics involving cosmic rays and gamma rays, and there's really exciting work being done in condensed matter experiment and theory as well. We've got awesome research going on in spintronics and photovoltaics and high pressure physics, and there's biophysics as well in our department. So there's all kinds of stuff. But going to the Astro Group, where I'm more familiar, we're a relatively new group. We became physics and astronomy in 2009, and the colleagues who've joined us since that time are awesome. We've got people doing work in cosmology. Kyle Dawson, Zheng Zheng does work in galaxy formation. Gail Sosowski is spokesperson for the Sloan Digital Sky Survey, which in its new incarnation is mapping out stars in the galaxy to an unprecedented degree. Anil Seth is working on hunting for black holes in the centers of galaxies, large and small. And I heard in some excitement that he may have access to James Webb Space Telescope data, which is really exciting. This is the cutting edge there. And Dan Wick does X-ray astronomy, looking at some of the largest things in the universe, galaxy clusters, which can reveal the nature of dark matter. And so we're a really exciting group, and we've got all kinds of opportunities. People are doing really cool things, and students join us to do that. I'm working with a student on a fun project on finding dusty debris around stars in a new and fun way. And dusty debris are the signposts of planet formation. So that's the kind of thing that I'm doing. So a really nice thing about joining us is that there is this focus on doing research and being part of research at all levels. It gives the signature experience for undergraduates and graduates at the University of Utah, and I think they're really great opportunities. So, sorry, I've spoken too much and too incoherently on all that, but yeah,
Oh
I
no, it
hope
was
I hope
great.
you get some enthusiasm
No,
there.
it was just fine. So we do have one comment, and it's just from Joan thanking you, and she says you're always a joy to listen to. So
Oh, well, thank you. That's nice.
with that, unless there's any other questions, I'll just end the live stream, and then I hope everybody has a good night. And Ben, it was great uh, listening to you and talking to you and stuff. I hope everybody else had just as much fun as I did. So I'll end the live video, and everybody else can have a good night. Thank you. Goodbye.
Thanks a lot.